In this screencast, we'll discuss the concept of ratio control. Ratio control is a type of feed-forward control. Feed-forward means that we will measure the disturbance variable, which here is the mass flow rate of stream 1, and we will adjust the manipulated variable. This is in contrast to feedback control, where we measure the control variable and then adjust the manipulated variable. Ratio control is used to hold two streams in a fixed ratio. So in the blending process, we've been using the mass flow rate of stream 1 is 1 kilogram per second, and the mass flow rate of stream 2 is 3 kilograms per second. So the ratio is W2 bar over W1 bar is 3. So the idea is that the disturbance variable might change. W1 might change, but then we should change W2 to hold that ratio fixed at 3 so we don't appreciably change the composition in the tank. Now let's consider a block diagram view of ratio control. So we'll have the effect of our disturbance variable, which we will refer to here as W1 of S, and that will affect our process through transfer function GD, but the process will also affect our outcome. So we'll consider the volume in the tank here, which will be affected by both W1 and W2. So we'll add to the effect of W1 the effect of W2, our manipulated variable. So we'll use the transfer function GP for process to express that effect of W2. So here's our process. We have a manipulated variable, we have a disturbance variable, W2, W1. And in ratio control, we are going to add a feed-forward loop where we measure the disturbance variable. And in this particular form of ratio control, we will multiply W1 by our desired ratio, which here would be 3. And this will give us a set point value for W2. And we will compare that in a feedback loop here to the actual value of W2. And then we will compute the error. So if those two do not agree, if we're not in our fixed ratio, then we will use our feed-forward controller, which here we call GF, to command W2. So we are performing feed-forward control by taking the value of W1 and using it to calculate W2, but within that strategy, we also have this feedback loop. One thing to notice here is that although W2 is our manipulated variable, that's no longer really an input to the process. We've closed a feedback loop around that. So now we really only have one input, which is W1, our disturbance variable. So with this block diagram, now we can calculate a transfer function to figure out how V depends on W1. So let's start off and say V of S equals GD times W1 of S plus GP times W2 of S. And then in addition, we will calculate that W2 of S equals GF times E, but E is just W2 set point minus W2, and W2 set point is R times W1 of S. Then we'll subtract W2 of S. So now we can solve for W2 by combining terms, W2 as a function of W1. And now that we've solved for W2, we can plug that back into our expression for V of S. And now we have a transfer function for how V of S depends on W1 of S.